Hello, everyone. This is Adam Pintar with the ASQ Statistics Division. Welcome, and thank you for joining us. Our speaker today is Joe Conklin. Joe is a mathematical statistician in Washington, D.C. He earned his master's degree in statistics from Virginia Tech in Blacksburg and is a senior member of ASQ. Joe is also an ASQ Certified Quality Manager, Quality Engineer, Quality Auditor, Reliability Engineer, and Six Sigma Black Belt. The webinar today will be about statistical process control, an overview and basic concepts, and if you're planning to take the CQE exam, what you need to know for that exam. There will be another set of slides, a more comprehensive set of slides that accompanies this presentation that will be available on the Statistics Division website in the near future as well. So this presentation will be on YouTube afterwards, and the additional set of slides will be on our division's website. All microphones other than the presenters have been muted, so if you have any questions or comments during the webinar, please use the questions interface in the GoToWebinar control panel. Joe will address questions at the end of the presentation. So now I'll hand things over to Joe. Thank you very much.
Welcome to the webinar. Congratulations on trying to acquire a quality credential with a long history. My former supervisor and mentor, Mike Mazu, was scheduled to be a co-presenter but is joining us in spirit today. Mike is a fellow of ASQ, a principal of MJM Associates in Newburgh, Indiana, and has been in the field of quality for almost as long as there has been a CQE. The slides you see today have benefited extensively from the training materials he regularly uses. The webinar is divided into two parts, one part for presentation and a second part for Q&A. One is, since we cannot cover all the helpful ground in a single 1-hour webinar, Mike and I have prepared two sets of slides for you, as Adam has explained. One is the presentation set we are going through now, and the other is the detailed study set that you'll find the link to on the last presentation slide. Statistical Process Control, or SPC for short, is a quality control and improvement strategy. There are 5 key features of SPC. SPC is prevention-focused, data-driven, graphic-centered, operator-run, and a way to identify quality problems and challenges. What separates SPC from other important and valuable quality-related data efforts is a relatively greater emphasis on the role and participation of process operators, more real-time on-the-spot analysis, and preventing problems versus explaining afterwards why they occurred. A helpful way to understand SPC is to look at the definitions of statistics, process, and control. Statistics is the art and science of collecting, analyzing, and interpreting data. A process is the combination of people, equipment, material, procedures, environmental conditions, and measurement that combine to produce a good or service. Control is a method for achieving conformance to requirements, or reducing the difference between what is expected and what is obtained. When SPC is implemented well, some of the benefits you should expect are reduced defects and nonconformances, a more stable, predictable process, a better ability to match production to the right process, an improved understanding of the implications of process changes, and an increased sense of employee involvement and ownership. SPC exists because variation exists. Variation is the tendency of outputs to differ in their characteristics even if consecutive units are produced under the same or similar conditions. In other words, no two examples of a good or service, even those produced back to back, are ever exactly alike in all respects. A key principle of SPC is that variation is present in all processes. Variation occurs in more than one form. Every process has a minimum amount of variation as a consequence of its design. This minimum amount is unavoidable and is the result of many small causes that combine in random ways. Identifying individual causes in this context is neither practical nor economical. Call this form inherent or natural variation. Variation can also reflect causes that are not built into the process design. They show themselves as interruptions or disruptions. These causes tend to be few in number, large in effect, and economically worthwhile to identify and then to remove or reduce. Call this form special or assignable variation. To sum up a little, variation exists in all processes as a mixture of inherent and assignable forms. SPC looks for evidence of assignable variation so it can be removed or reduced. As a popular example of the distinction between inherent and assignable variation, consider driving a car. Imagine a daily commute to work or a trip to some store you visit regularly. If you were to time consecutive trips, you would find they do not all take exactly the same length of time. The times vary slightly. What is going on is the combination of how well all the parts of the engine work, weather conditions, the number of other vehicles sharing the road, the condition of the road. If you stop to list the different causes, it would be a very long one. These hundreds of causes vary in their effect and how they combine each time, leading to different travel times. Inherent variation in action. It is easy to imagine a selective set of causes, an accident, a flat tire, or a dead battery, that increase your travel time way beyond normal, or perhaps cancel a trip altogether. Assignable variation in action. We cannot drive a car without dealing with engines, weather, traffic, and road conditions. They are built into the process. Through strategies such as defensive driving and preventive maintenance, we can keep accidents and breakdowns from being a regular part of reaching our destination. We can reduce or remove the assignable variation. So where can variation occur in a process? The answer is anywhere. I want to draw your attention for a moment to the bottom bullet about measurement systems. A successful SPC project requires a stable and precise measuring system. One reason why SPC projects sometimes fail is because of an inadequate measuring system. I will come back to this point later. How does assignable variation show up in a process? How can we tell it is there? There are three classic patterns. The easiest and fastest way is to plot process data in time order. One classic pattern is the sudden shift. In this pattern, the process moves at one average level, and then in a very short time moves to a different average level. The process appears to jump. A second classic pattern is a gradual drift. The process moves from one average level to another, but the change is a gradual drift over time. The third classic pattern is cyclical. The process alternates from low to high to low in a periodic fashion over time. Speaking of plots, here is one you want to know: a control chart. A control chart draws a picture of what is going on in your process. Think of it as a stethoscope for your process. It shows the variation profile. On the horizontal axis, you see different time periods. Control charts are concerned with how a process runs in time order. On the vertical axis, we plot sample results that depend on the type of chart. You will see more details later on, and there are more in the study slides. The center line on the control chart shows the process average or expected value. The area bounded by the upper and lower control limits is where we find the zone of inherent variation. Control charts have several purposes. Three big ones are signaling the need for corrective action, maintaining process stability, and establishing process specifications. With a control chart, one of two basic conclusions applies at any given time. Either the process is in statistical control or it is out of statistical control. In statistical control is what we want. The evidence of statistical control is indicated on a control chart by random movement between the control limits. The majority of the plotted points are near the center line, and a few points are near the control limits. A control chart is designed so it is possible for a very small percentage of points to be outside the control limits when the process is in statistical control. But in practice, a useful rule is to say that no points should be outside the limits. When the process is in a state of statistical control, the only way to improve performance, if the output is unacceptable, is to redesign the process. This is a management decision and not an operator decision, although operators should be involved in improving the process if that is necessary. Intervening in the process when it is in statistical control, if these interventions are not part of a long-term redesign, is likely to make matters worse. When a process is in statistical control, the outputs will be stable and predictable. This does not mean they will all be exactly alike in all respects. It means that histograms of the output values will be similar from hour to hour, day to day, week to week, or over whatever time frame makes for sensible comparisons. A process is out of statistical control when points plot outside the limits, the points hug closely to the center line, the points hug closely to one of the control limits, or is there some non-random pattern, such as a sudden shift, gradual drift, or cycle. There are rules you can use to tell if a process is out of statistical control. A run rule says if 9 or more consecutive points are on the same side of the center line, then the process is out of statistical control. A trend rule says if 6 or more consecutive points move either all up or all down, then the process is out of statistical control. For simplicity, the immediately preceding discussion assumes the process has a fixed, constant target, but not all processes are like this. Some processes involve tools that work gradually with time. They have a trend built into the basic design. Some pieces of measuring equipment have small but distinct cyclic variations in response to changes in temperature and humidity. If some non-random pattern is part of the process design, the preceding discussion still applies, but the analysis changes. In these cases, we take the process values we observe and analyze their difference from the value we expect under current conditions. If you're familiar with the concept of statistical modeling, this is like fitting an equation and analyzing the residuals. This is a good place to make some important summary points. Being in statistical control means the process is stable and predictable. It does not necessarily mean the output is good. It is possible for a process to stably and predictably produce bad output. What statistical control buys you is knowing what type of improvement makes sense, either a long-term redesign or a less radical on-the-spot corrective action by the operator to remove an unnecessary source of variation. Also, if you need to improve a process, starting with one that is stable and predictable makes it easier to tell whether a proposed change will make a difference. It is easy to confuse control limits with specification limits. It is worth some time to make sure we are clear on the difference. You can think of control limits as the voice of the process. They tell you what to expect from the process given the current design. The specification limits are the voice of the customer. They are what the customer wants. The process does not know what the customer wants. Management has to create and support an environment where the right processes are matched to the right requirements. There are 4 possible states for a process. The ideal state is for the process to be in statistical control and in specification. The customer is happy, and we as the supplier are meeting requirements in an efficient and consistent manner. If our process is in statistical control but out of specification, the customer is not happy. As a supplier, however, we stand the best chance of making things better because we start with a stable process and can figure out most quickly what improvements are the best. If our process is out of control and in specification, the customer is happy, but as a supplier, we are worried. The process is inefficient and may require extensive babysitting and hand-holding. The atmosphere is one of frustration. If our process is out of control and out of specification, nobody is happy. As a supplier, we are not sure what is happening next. We are not sure which changes are the best improvements, and the atmosphere is one of panic and chaos. Of the 4 states, this last one demands the most immediate attention. The moral here is that we need to care about both internal and external customer requirements for the greatest chance of long-term success. There are 2 large and useful categories of control charts: variables and attributes. They are named for the type of data plotted on the charts. When you hear variables data, think measurements. Measurements of time, measurements of dimensions, or measurements of some physical, electrical, or chemical property. Variables data may have fractional values. Variables control charts are used in pairs. One chart of a pair tracks the average performance of the process. The other chart of a pair tracks the variation. There are 4 common pairs of variables control charts. They are X-bar and range, X-bar and standard deviation, median and range, and individuals and moving range. X-bar, median, and individual charts track the process average. Range, standard deviation, and moving range track the process variation. The charts are named after the nature of the data they plot. X-bar charts plot the arithmetic average of a sample of units from the process. Median charts plot the median of a sample, and individuals charts plot the measurement of a single process item when it is not practical or economical to measure a sample of several items. A range chart plots the difference between the largest and smallest measurements in a sample. Standard deviation plots plot the standard deviation, and moving range charts plot the absolute value of the difference between the current sample value and the immediately previous one. When you hear attributes data, think counting. Attributes data in SPC applications is a count of the number of faults or defects or a count of the number of units with at least one fault. Defectives. A defective unit may have more than one defect. This type of data is counted, not measured. Only whole numbers make sense, not fractional values. There are 4 common types of attributes control charts: percent or fraction defective, number of defectives, number of defects, and number of defects per unit. With attributes control charts, a single chart tracks both process average and variation. A percent defective or P chart plots the percent or fraction defective in a sample. If a sample contains 100 units and 10 of them are defective, the P chart will plot 10% or 0.10. A number of defectives or NP chart will plot the number 10. A number of defects or C chart plots the number of defects in the sample. If the sample consists of 10 units and each unit has exactly 2 defects, the C chart will show the number 20. A defects per unit or U chart will show the number 2.0. To ensure comparability between time periods, NP and C charts require a constant sample size. P and U charts may have varying sample sizes across time periods. To collect the data for attribute control charts, some defects have to have already occurred. That means that compared to variables control charts, attributes control charts are not as quick to react to assignable variation. Other important distinctions between variables and attributes control charts are: variables data contains more information per sample than attributes data. Therefore, sample sizes for variables data can be smaller by comparison. Since it is usually easier to count something than to measure it, variables control charts tend to be more complex to set up and manage. Variables control charts are ideal for operations involving critical product characteristics, demanding the fastest reaction to evidence of assignable variation. Attributes control charts are ideal for applications involving several equally important characteristics that are most easily managed and summarized as a group. This tends to be the case in applications involving business processes such as accounting, inventory, or training. Control charts require sound design and construction. The principles of these can be summarized here, but you should refer to an SPC manual or a textbook if you need more detailed guidance. Control charts track critical or important quality characteristics where the operators can take action to respond to unwanted variation. Before implementing a control chart, the measurement system should be checked to ensure it provides precise data. Here is where the concepts of gauge R&R studies play a vital role. The sampling method for process data has to match the type of chart, and samples should be taken according to a standardized procedure. The sampling frequency depends on how long a period of time provides an opportunity for assignable variation to occur. The shorter this time period, the more frequent the sample should be. Each item in a sample should be collected over a short enough period of time so each one reflects the same or very similar process conditions. In SPC, this is referred to as the concept of a rational subgroup. Most importantly, the operators need a reaction plan telling them what to do if the control chart indicates the process is out of statistical control. We will say more about reaction plans in a few moments. To implement a control chart, we need an initial set of data from the process over a period where the important sources of variation have a chance to operate. We take our measurements or counts, calculate the values to be plotted on the chart, and plot them. We should also document any special or unusual events observed during data collection. Once we have recorded the data, we calculate the center line and control limits. Then we evaluate the chart for statistical control. If we are implementing a variables control chart, the chart that tracks variation is evaluated first. After removing or reducing causes of assignable variation there, we next tackle the chart that tracks location. You will find formulas for calculating control limits in the study slides. If the process shows statistical control after the initial data collection, it and a reaction plan can be turned over to the operators. If the process is out of statistical control, we need to find the causes, remove or reduce them, and start over with a new data collection. Control limits, once set, are not forever. When the process is redesigned or improved, new control limits are necessary. If the quality characteristic becomes more or less important, the type of chart may change, and this will change the control limits. If the customer requirements change, it may also be necessary to change the control limits. In all these cases, the design and construction phase starts over. Where do we find sources for reaction plans to go with our control charts? The short answer is almost anywhere. Customer or vendor documentation, industry standards or best practices, benchmarking of other plants or divisions in the company, the lessons of cross-functional process improvement projects, process capability studies, or designed experiments are a few possibilities. Reaction plans may be simple, as in calling the supervisor, maintenance, or engineering, or more complex, as in checking equipment settings, verifying tooling, or recalibrating. You have heard a lot of information about SPC, how it works, and its benefits. It is a good idea to start winding up with some thoughts about how SPC fits into the general picture of quality improvement. A useful distinction is between SPC principles and SPC tools. SPC principles, customer focus, fact-based decisions, an emphasis on prevention, and the importance of employee ownership and involvement are also important general principles in the field of quality and are always in season. Control charts have great power, flexibility, and widespread application. They can be an important part of solving a quality problem, but they may not be the entire solution. When confronting a quality challenge, the right question to ask is, what tools should be on my team, and how can control charts work together with these other tools for an optimal solution? We close our presentation with a brief consideration of two special purpose charts. The first is Shannon pre-control charts. Pre-control charts are based on a customer specification band for a process. The specification band is divided into 4 equal parts. The middle quarters are colored green. The top and bottom quarters are colored yellow. The region outside the specification band is colored red. There are 2 sets of rules, one set for qualifying a process and another for continuing to run. The rules say how many consecutive units can fall into a given color before restarting or requalifying the process. The colored zones work like traffic lights. Green is safe, yellow is caution, and red is stop. You will find more details in the study slides. Pre-control charts are not a shortcut for problem solving. There is a considerable body of problem-solving techniques to accompany these charts that the Shannon organization has developed over the decades. If you slap a colored chart on top of a process but skip the problem solving, all you are likely to end up with is a colored chart and a bunch of bad product. The second type of special purpose chart is suited for short runs. That is a production environment characterized by high product mix and low product volume. A short run chart tracks multiple runs of product with varying settings or specifications. The process may work the same material to make parts of varying dimensions. The pattern of variation is the same across runs, but the tooling is set to whatever dimension the customer order calls for. We can subtract the nominal dimension from the observed dimension and plot the differences to control the process. Or it may be possible to transform products of varying dimension, setting, or measurement so that the process data is on a standardized scale. Then the standardized values are used to control the process. We have covered a lot of ground. It is now time for your questions. I wish you well if you're studying for the CQE exam and hope to count you all eventually as holders of ASQ's original credential. One of my motivations for presenting this webinar is I will soon celebrate the 30th anniversary of earning my CQE. It is a moment I recall with pride. May it be the same for you. I hope your journey in quality, however long, is both personal and professionally rewarding. I'll now take your questions.
So there are a few questions. Joe, would you like me to read them? They've been typed into the questions interface, or would you like to read them?
Please read them, Adam, and I'll answer.
Okay. So the first question is this. Isn't SPC rather more like a patch or temporary remedy when you take action so that it would not correct design problems? Of course, I will understand it will help dealing with variation.
The corrective action that an operator takes in response to a control chart is kind of like the action, getting back to my car example, since I know that accidents or flat tires or dead batteries are possibilities, I apply ongoing corrective actions as I'm driving my car to be a defensive driver, and I do preventive maintenance. So those corrective actions don't get to the design of how my car is put together, but at least in my mind, it's more than just a patch. It's a vital and efficient action that allows me to achieve the goal of my process without having to redesign my car completely. I think a similar idea applies in general to a production environment.
Question number 2. Are control charts sensitive to non-normal distributions? And if so, how do you utilize control charts for non-normal data?
Well, the answer to this question falls into 2 parts, I think. First, it depends on the type of chart you're talking about. If I'm implementing a variables chart and it's an individuals chart, then that chart is sensitive to the normality assumption. If I'm dealing with an X bar chart, it's somewhat less sensitive. One useful principle that Donald Wheeler articulates very well in his SPC books is that regardless of whatever the distribution of your process data is, whatever the 3 sigma limits are based on that distribution, those 3 sigma limits have a good track record of balancing risk, so that if something is beyond those 3 sigma limits, it's usually a good idea to spend some time to figure out what's going on. If you're dealing with an individual's control chart and you have reason to believe that your data is non-normal, the best general answer is to use histograms, plots, transformations to try and identify the distribution that best fits it, and then calculate the 3 sigma limits that are appropriate to that distribution. Computers are extremely helpful in this effort.
Thank you. The third question, where are the study sides the invites say are included? Yes, those are, the URL is on the slide that's still up there, the asq.org/statistics. So, sorry, Joe, I'll take this question. They're not there yet, but they will be in the near future. Okay. The next question, how do you set control limits when the population is less than 20?
Well, I would need a little bit more information to answer that. Is it less than 20 because this is a new product I'm thinking of marketing and I'm doing a small prototype run? Is it 20 because it's something that's not ordered very often and I only make a run of 20 once in a while? I think those are the 2 basic possibilities, so I'll handle each of those as a separate part. If I'm starting up a new product and I have a production run and the process I'm using is, the facts about it would suggest that a control chart is worth looking into, what I might consider is starting out, taking those samples, those 20 units, measuring them, and constructing an individual's control chart and see if it tells me anything. That might give me some information and guidance for what else I need to do to get the process ready for prime time. If the situation I'm in is it's a standard product, it's been around for a while, but it's ordered in small quantities, I may be in the short run the situation I described a few minutes ago, and if possible, I would look for opportunities to use either those entire 20 or a sample of the 20 as a point for a short run chart. This assumes that there are similar products out there that follow similar patterns of variation, so there's some comparability across products that enables me to do this.
Thank you, Joe. Next question. Can you use SPC if the data is non-normal and has to be transformed to measure process capability? How would you use SPC control charts for that example?
Okay, well, I think I answered this already.
Okay, all right. That was the non-normal question. You're right.
Yeah.
What are some best practices for when to take action on data points outside of control limits, i.e. avoid overreacting?
Well, the short answer is the best general rule is use 3 sigma control limits on your chart. Get familiar with the conditions that indicate out of control that we discussed, like points outside the limits and non-random patterns or runs and trends, and then only react when you see those signs on the chart. There may be a little bit more to this, and so I'll go out and try to do some educated guessing here. If this process hasn't had a control chart before, and I'm implementing it for the first time, if I have a lot of pressure, encouragement, or incentive to do this as quickly as possible, I may collect my initial data over a period of time that's too short for all the important sources of variation to show up. Well, if I don't have all the important sources of variation accounted for in my data, then my control limits will be too small. So I may be reacting more. The chart may be telling me to react more often than I should. That's a situation that would need to be tested and checked out and looked into. If that is what's going on, the general answer would be hold off implementing that chart until you've collected data over a longer and more representative period of time to capture all the important variation. Any others, Adam?
Sorry, I was on mute. Sorry about that. I forgot to take it off mute. The next question is if
your last one was really easy.
Okay. If we produce about 4 batches per week and there is a lot of inherent variability in our process, what chart should we be using? So that was part 1 to the question, and there's a second part to the question. Our rational subgroups contain about 6 samples usually. Although we are well within specifications and X bar R chart is out of control, but an IMR chart shows statistical control, there is a concern with the IMR chart because the values are averages.
If the values are averages, you shouldn't be using an IMR chart. What may be going on here is that, let's say you have a part and you measure it at 4 or 5 different points, but the official measurement for the part is some function of those 4 or 5 contributing things. Well, from that perspective, if the definition of the representative measurement for the part is those several components combined some way, then I would say it's okay to use an IMR chart. However, if what you're doing is you're taking discrete units in the sample at a given time, you're measuring the units each one, and then calculating an average for a group of units in a single sample, then the IMR is not intended for that. I'm not surprised that if you had an IMR chart that was set up for just individuals and it appeared to be less sensitive than an X bar R chart, that would not surprise me. As a general rule, X bar R charts are more sensitive than individuals charts because when you think about it, at each sample you have more information behind that point. As to the first part of the question, which I think was something like they have a lot of inherent variation. It's not unusual for a process to be in statistical control in the sense that only what's going on is inherent, but the magnitude of that natural variation is larger than larger than what would be allowed in order for you to have conforming output. If that's your situation, the inherent variation is too large. Your basic strategic choices are either improve the design of the current process through tools like perhaps a process capability study or design experiment, or maybe an engineering redesign. Either redesign that process or switch the production to another one where the variation is smaller and is consistent with acceptable output. I hope I didn't miss anything.
All right. The next question, are control limits just plus and minus 3 standard deviations, or should one use Shewhart constants?
Shewhart constants, which by that I mean I believe it's in Table E of the Quality Control Handbook. If that's what you're referring to, those constants are intended to give you 3 sigma limits. Sometimes, if there are processes that have a natural lower value, like it can't go below 0, the formula may crank out that if you calculated a lower 3 sigma limit, it would be negative. That's most common, I think, with attribute charts than variables ones. But if that happens, then the lower limit would be truncated to 0. So in that special case, it wouldn't be technically plus or minus 3 sigma. We don't draw a control limit in a region where it doesn't make, where we could never see process values there.
Okay. The next question, can you explain how an organization would do a control chart based on CPK data?
I don't see a way to do that if all I have is the CPK number. To do the control chart, I would need the data behind the CPK number. Am I mishearing the question?
I have read as is. We'll move on. Can you describe scenarios where it would be of benefit to use EWMA charts?
EWMA charts are well suited for processes, and chemical processes are the classic example of this, where processes that have memory. Traditional SPC theory assumes that the samples are independent. That means when you take your sample, the data tells you something about that sample, but it doesn't have any information or predict what went before or what after, or what comes after. Chemical processes in particular tend to evolve as they run. That means if you look at the run chart of some characteristic from a chemical process and pick a point on there, you'll be able to make an informed prediction or claim about what was going on in the process a little bit before that point and a little bit after that point. So if your process has a memory, if what's going on at time X has a big influence on what I see at time X plus 1 or X plus 2, then EWMA charts are an excellent tool for creating control limits that respect that type of behavior.
All right, thank you. Suppose you were using an individuals chart. Could you perform a Box-Cox class of transformation on the data before calculating or plotting the control limits and observed points?
Yes, the short answer is yes, I can do that. The Box-Cox class of transformations comes from the 1960s, as I remember right. Since then, later research has provided us with a larger and more exotic collection of different transformation families, so you wouldn't need to confine yourself to Box-Cox. You could, experiment with some of the other possibilities to see what does the best job. That said, if I were on a desert island and had to pick one thing to do that sort of work, it would be Box-Cox.
All right. What do you do if you see small trends around the control limits but are well within spec?
Are we talking about an individual's chart or an X-bar chart?
This is a completely separate question from the previous one, and it does not specify that.
Well, it depends on what situation we're talking about. I'll assume that we're dealing with an individual's chart. Could you reread the question, Adam?
Yes. What do you do if you see small trends around the control limits but are well within spec?
Small trends. Okay, so I have my individuals chart and I have my control limits, and I'm assuming the control limits on this individual's chart are well within the spec limits. So I'm looking at the points and they're all within the control limits, but every once in a while I find a local group that violates the trend rule. So what do I do? Okay, well, if this is the first time this has happened, if I see that small trend, I should try to investigate and account for it and assess it in terms of what are the consequences if I let it go? What options would I have to reduce or eliminate it? If it's the second or third or multiple times it has happened and it's for the same reason, I could be in a situation where if I have limited resources and I have to prioritize which assignable variations I go after, I may not forget about this particular one, but I may put it towards the bottom of the list and schedule it for more work at a later time once I've handled more dramatic and pressing cases. I hope that helped. It's kind of hard to give a good, compact, general answer to something like that.
Okay, well, so we'll move on. The next question, is there still too much controversy in SPC methods?
I'm struggling to give a short answer to that one. Okay, I think I would answer that with the following points. The theory behind SPC, the statistical theory, has not stood still. Research has been ongoing, and the statistical community, whose research specializes in control charts, they occasionally come up with new variations on old ideas and completely new concepts. So there's controversy in the sense of what does this mean? How do we use it? Should we disseminate it for general use? Where does it fit? There's that kind of discussion. You could call it a controversy, I guess. There's another situation I'm thinking of. Usually, when you're talking about control charts, let me say, maybe not usually, but more than just once in a while, you have more than one choice of what control chart to use. For example, depending on what gauging you want to use for this part, you might use an attributes chart or a variables chart, and there might be some controversy within the plant about which one are we going to go with. Do we use the attribute one because it's quicker and cheaper, or do we go with the variables gauge because this is a very vital characteristic and we need the maximum amount of information? And thirdly, in the consulting area of statistical techniques and quality, consultants, depending on what type of industry they work in and what type of problems they encounter, being human like the rest of us, they can develop their own instinctive sense about what their favorites are. And if I'm a consultant, my favorites may not be the same as your favorites. And so you could have some give and take and back and forth to try to make it my case versus yours. In any of these situations, whether it's what do we do with new research, or what's the best option for the plant, or is it consultant A or consultant B? As long as the discourse is civil and respectful, I think we're all served by having as much of it as possible.
Okay. All right. Thank you. The next question. Is it acceptable for an organization to deliver a product that is out of control limits but within specification limits?
Okay, well, this gets back to my discussion about the moral I said in discussing the difference between specification limits and control limits. I think the best general answer is there's more than one customer, okay? There's the external customer who signs the check, and we have to please him. There's no question about that, him or her. But there's also the internal customers, the people who work inside the plant. I have a management risk if I ship product the customer likes, but it's from an out-of-control process. I have some risk that I'm allowing some inefficiency, which could carry some increased long-term costs, and I'm also risking a situation where eventually I can't get that inspect product with a lot of hand-holding and babysitting of the process. Well, I think most of us would agree that the people who are in the middle of a process like that and are expected to run it are not going to enjoy coming to work after a while. They're going to start feeling frustrated, and their commitment to their work is probably going to suffer. So I may be in a situation where I may not have much choice for this given moment for that to go. But as a general rule, I wouldn't want that state of affairs to continue indefinitely. If I do, I'm accepting some risks with consequences I might not like.
All right. There's just a couple more questions left. We'll try to get through them quickly. I know it's the top of the hour now, but let's try to get to the last few questions. Any suggestions for executing SPC in a continuous production environment in which customers are capable of receiving different levels of quality or specifications?
My short answer to that would be short-run charts. And I believe there's an excellent article on those in the Juran Quality, or I guess it's now the McGraw-Hill Quality Control Handbook.
Okay. In an X-bar R chart, if I have a long-established CPK equals 7, when I see an out-of-control point, what reaction do I take? Say there's little room for improvement.
Well, I have an answer, but it's not the one you might be expecting. If I have a CPK of 7, that tells me I may have some specification limits that are very wide. I could be missing a marketing opportunity here. If I offer the customer who has given me these wide specification limits a deal where I'll accept a tighter specification because I can do that for the same price, I might get some interest and some profit in my bottom line. So the first question I would ask is a non-statistical one. Can we narrow these specs and offer an attractive deal to our customer?
All right. The next question, how did the original classic Westinghouse out-of-control indicators expand, and are the newer indicators valuable, and why so?
I have to be honest with you, you've caught me on that one. In that particular one, I've heard of the old ones, I don't know what the new ones are. So my the best I can tell you is I'd like to help you, but at this point I don't know the difference between the old and the new, so I probably had better not comment.
Okay. Next question, is it prudent to implement control limits on a process where the CP is less than 1, or should one reduce variation first to improve CP to be greater than 1, then implement control charts?
Okay, and my answer is go through the initial data collection for implementing a control chart. Remove the assignable, evaluate the chart, remove the assignable causes, collect some more data, go through that cycle. When you have the variation reduced and get the CPK above 1, then you're in a situation where you can hand that control chart off to the operator. So the short answer is, if you don't have a control chart already, I wouldn't put one out there until you've done some improvement behind the scenes and gotten the CPK better. If the process was running above a CPK of 1 for a while, but it's gotten worse, you may not be in a situation where you can pull the control chart down, but you may need some intense fast-track problem solving that's going on to get to the bottom quickly as to what may have caused the performance to deteriorate.
Okay. Thank you very much, Joe. That was the last question. It was a very good presentation. Now we ask that our attendees complete the short survey available within GoToWebinar. And a recording of the webinar will be available within a few days on the division's YouTube channel at youtube.com/ASQ Stats Division. Please be sure to share this webinar and our other archived webinars with your friends, coworkers, and colleagues. Also, we encourage you to check out the division's LinkedIn page as well as our events calendar, which can be viewed at asq.org/statistics for the latest news on webinars, conferences, and many other topics. I mentioned this earlier, and I'll mention it one more time. There will be an extended set of these slides that Joe went through today on the division website, asq.org/statistics. They're not there yet, but they will be available there in the next couple days as well. That's all the time we have for today. Thank you again, everyone, for joining us, and thank you very much, Joe, and I hope everyone has a wonderful afternoon.